Have you ever seen something just blow up overnight? A video, a meme, anything? Well, today we're cracking the code on the math behind that explosion. We're talking about exponential functions and how their simple graphs tell this incredible story of slow, quiet growth that suddenly goes completely vertical. So let's start with a weird question. What on earth could a viral social media post and bacteria growing in a petri dish possibly have in common? I know, it sounds random, but the answer is actually a really elegant, powerful mathematical idea. And there it is. They both follow the exact same pattern of exponential growth. It's this unique kind of change that starts off so slow you barely even notice it, and then, bam, it just takes off like a rocket. Understanding that pattern? That's what this is all about. So here's our game plan. First, we're going to look at what makes this growth so powerful in the first place. Then we'll build our own basic graph from scratch. After that, we'll check out its mirror image, what we call decay, and then we'll put different functions into a little base race to see who wins. And finally, we'll cover two super common traps just so you can sidestep them completely. Sound good? Let's dive in. Okay, first up, the power of growth. Before we even think about plotting a single point, we've got to get a solid handle on the basic definition. Trust me, the rules behind this function are exactly what gives it its incredible power. So here it is, the official blueprint. F of x equals b to the power of x. The key, though, the real secret sauce is in the rules for that base b. Number one, it has to be positive. And number two, it can't be 1. That's it. Just those two simple rules create that iconic, explosive shape you see in every single exponential graph. All right, let's get our hands dirty and actually build one. We're going to start with the most classic example there is, f of x equals 2 to the x. Seriously, if you can wrap your head around how this graph comes together, you'll understand the foundation for pretty much every exponential growth curve out there. So how do we graph this thing? Well, the easiest way is just to build a table of points. We'll pick a few x values. Let's do some negatives, 0, and some positives. And we'll just plug them in. So if x is -2, 2 to the -2 is 1/4. If x is 0, 2 to the 0 is 1. That's a big one. And if x is 2, 2 squared is 4. See? Each little calculation gives us another coordinate we can put on our graph. And now for the fun part. We just take those points, plot them on the graph, and connect them with a nice, smooth curve. And right away, you can see that signature shape. It's creeping along, almost flat on the left side. It cuts right through that super important point at 0, 1, and then it just rockets straight up on the right. That, right there, is the picture of exponential growth. Now let's break this down a bit. Let's talk key features. The domain, that's all the possible x values. Well, you can plug in any number you want, from -infinity to +infinity. But the range, the y values you get out, that's only positive numbers. And this leads us to a really, really important idea, the horizontal asymptote. It's basically a line that the graph gets super, super close to, but never actually touches. And for this basic function, that line is the x-axis itself, the line y equals 0. The curve gets infinitely ridiculously close to 0, but it will never, ever get there. Okay, so we've seen what happens when our base, b, is bigger than 1. We get growth. But what if it's a fraction? A number between 0 and 1. Well, that's when we get the total opposite, the mirror image of growth, something we call exponential decay. Just look at these two side by side. On the left, you have decay. It starts way up high and then gracefully falls towards 0 on the right. On the right, you have our familiar growth function, starting low and shooting up. They're perfect mirror images of each other. But here's the cool part. Look closely. They both pass through the exact same point, right there at 0, 1. So what's the link? What's the connection? Well, it's actually a pretty simple exponent rule you might remember. A fraction like 1/3 to the power of x is the exact same thing as 3 to the power of -x. And in the world of graphing, what happens when you make the x negative? You get a perfect reflection across the y-axis. So decay isn't some brand new scary thing. It's just growth, looking at itself in the mirror. All right, now for some fun. What happens if we have two different growth functions? What if we change the base? Let's stage a little competition, a base race between 2 to the x and 4 to the x. Who do you think wins? Okay, check this out. On the right side of the graph, where all the x's are positive, the bigger base,
4 to the x wins, and it's not even close. It is way, way steeper because you're multiplying a bigger number over and over. But look at the left side. Where the x's are negative, the complete opposite happens. The bigger base, 4 to the x, actually gets smaller faster. It hugs that x-axis even tighter than 2 to the x does.
So the main takeaway here is pretty simple. A bigger base just makes the graph more extreme. It shoots up faster on the growth side, and it dives towards 0 even quicker on the other side.
All right, before we wrap this up, let's talk about 2 common traps. I see these mistakes all the time, and if you can learn to spot them right now, you are going to be way ahead of the game. Okay, trap number 1. Please do not confuse exponential decay with having a negative base. They are not the same thing. On the left, you see decay. The base is 1/2. It's positive, and it gives us that smooth, predictable curve. On the right, you have negative 2 to the x. That is not an exponential function. Remember our first rule? The base has to be positive.
And the second big one is what I call the zero misconception. It just feels like the curve should eventually hit 0, right? But it doesn't. Remember that asymptote? The value of the function will get unbelievably close to 0, but it will never, ever equal 0. That's why the range is all numbers greater than 0, not including it. And this brings us right back to that viral video we started with. The amazing thing about exponential growth is that its doubling time is constant. So the time it takes to go from 1,000 views to 2,000 views is the exact same amount of time it takes to go from 1 million to 2 million views. It's just doubling. And that is why the growth feels so sudden and just absolutely explosive. So why do you need to know this stuff? Is it just for a test? No way. Exponential functions are literally everywhere. You can't do calculus without them. They model how money grows, how populations change, even radioactive decay in physics. Getting this now is building a foundation for so much of the science and math you're going to see later on. So I'll just leave you with this thought. The exact same math that explains a viral video is also used to model the spread of a pandemic. So take a look around. What else in your world, from your savings account to learning a new skill, might just secretly be exponential? Think about it.